guys, welcome back to another CalcFly video. We're back with another video. In this video we're going to be talking about question 6 from 2019 AP Calculus free response portion. Alright, so in this problem we're given 3 functions, and these 3 functions are twice differentiable. We're going to be using this givens, and also g of 2 is equal to h of 2, and they're all equal to 4, and also we're given this line, and also this line is a tangent to both g function and an h function at x equals 2. Alright, let's focus on part A. In part A it says we're being asked to figure out what is h prime 2. So if this line is tangent to both g and h functions at x equals 2, then the slope of this line has to be equal to both h prime 2 and g prime 2. Okay, so basically we can easily determine the slope of this line, which is equal to 2/3. So basically h prime 2 must be equal to 2/3. So that's the first problem. Okay. Then let's focus on part B. It says let a be the function given by a of x is equal to 3x cubed times h of x. So write an expression for a prime x and evaluate this expression at x equals 2. Alright, so before I do that, so part B, so h prime x is going to be equal to, if I apply the product rule, so I'm going to take the derivative of first function, which is 3x cubed, so it's going to be equal to 9x squared times the second function, and plus the first function itself times the second function derivative. Okay, then we're going to evaluate this expression at x equals 2. At x equals 2. So this is going to be equal to, if I clean up this board here, and this is going to be equal to 9 times 2 squared times h of 2 plus 3 times 2 cubed times h prime 2. Okay, so 9 times 4 times h of 2, which is given, which is 4 times 4, and plus 3 times 8 times h prime 2. We figured it out in part A, which is equal to 2/3. Okay, so if we calculate that, this simplifies to 9 times 16 plus 16, and this is going to be equal to 160. 160. Okay, that is part B. Alright, let's move on to part C. In part C, we're given that the function h satisfies this expression. Alright, and it is known that the limit x approaches to h of x can be evaluated using L'Hopital's rule. So basically, in order for us to apply L'Hopital rule, when we do the direct substitution, we need to be ending up with this following expression. So we call them indeterminate forms. So it could be either 0 divided by 0, or infinity divided by infinity, or 1 to the power of infinity, or 0 to the power of infinity. Okay, so when I do the direct substitution for part C, that's going to be equal to 2 squared minus 4, 1 minus f of x to the power of 3. Okay, so this top is going to be equal to 0. 0 divided by this expression. So in order for us to apply the L'Hopital rule, this bottom part has to be also equal to 0. So basically what I mean, I'm going to erase that, I'm going to rewrite it. So this limit also has to be equal to limit x approaches 2, 1 minus f of x to the power of 3 has to be also equal to 0. Okay, so if I rewrite this limit, I'm going to get that limit x approaches to 1 minus limit x approaches to f of x and to the power of 3, and this expression has to be equal to 0. So this expression is going to be equal to directly 1, and this is going to be just limit x approaches to f of x to the power of 3 and 0. So if I move this part to the right hand side, we get the limit x approaches to f of x is going to be equal to 2. So we got this. Okay. Then, so basically, we got this. That means that whenever I come across this expression, that also means that this f of x is, since f of x is continuous, so that means this expression, limit x approaches to f of x, has to be equal to f of 2, which is equal to 2. Alright, so we got the first part done. So let's move on to the second part. So, limit x approaches to f of x is going to be equal to just 1. Okay? That means f of 2 is also equal to 1, because we know that f function is twice differentiable. That means if a function is differentiable, that implies also it is also continuous at that specific point. So basically this is equal to f of 2 is equal to 1. Then since we know that since f is twice differentiable, that means f prime is also continuous. Okay? If f prime is also continuous, so I should be able to write this down. Limit x approaches to f prime x is going to be equal to f prime 2. Alright? So, limit x approaches to x squared minus 4 over 1 minus f of x to the power of 3. Okay. So if I apply the L'Hopital rule, we're going to get that. If I clean up this part. So after that, we're going to apply the L'Hopital rule. So let's remember the L'Hopital rule. Basically, I'm going to take the first derivative of top function and then also bottom function. But notice that I'm not going to apply the quotient rule for the derivatives. Okay. So limit x approaches to, if I take the first derivative of top, we get 2x. Divided by, if I take the first derivative of bottom, we get negative 3 times f of x to the power of 2 times f prime x. Okay, and this expression is going to be equal to also 4. Okay, so if I substitute 2, if I plug in 2, we're going to get 2 times 2 divided by negative 3 times f of 2 to the power of 2 times f prime 2. It's going to be equal to 4. So these two are going to cancel each other out. And what we're going to get is 1 equals negative 3 times f of 2. We know that f of 2 is 1, so the 1 squared is 1 times f prime 2. If I treat f prime 2 as like variable, if I solve this equation for that variable, what we're going to get is f prime 2 is going to be equal to negative 1/3. So we got f of 2 is equal to 1 and f prime 2 is equal to 1/3. Okay. So to be able to solve this part C, we've benefited from this given information because we know that f is twice differentiable, which means f prime is also continuous at the same point, which is x equals 2. Alright. So let's move on to part D. Before that, let me clean up the entire board. So the part D is a great application of squeeze theorem. According to the squeeze theorem, if you remember that. So we know that since g and h are differentiable functions, so we know that if any function is differentiable, that also implies that that function is also continuous. So we're going to be using this fact. Okay. So since g and h functions are differentiable, that means g and h are also continuous. So if they are continuous, I should be able to write these two statements. So limit x approaches to g of x has to be equal to g of 2, and also limit x approaches to h of x has to be equal to h of 2. So since since g of x is less than or equal to k of x is less than or equal to h of x, and notice that this k function is getting squeezed in between the g of x and h of x on this interval 1 less than x less than 3. So it follows from the squeeze theorem that limit x approaches to k of x has to be also equal to k of 2, which is going to be equal to 4, because g of 2 is equal to 4 and h of 2 is equal to 4. So that therefore k is continuous at x equals 2. Since we ended up with this expression, that means k is continuous at x equals 2. So basically for part D, we've used the squeeze theorem. That's the application of the squeeze theorem. Alright guys, thanks so much for watching. In this video, we've talked about question 6 from 2019 for your response portion. Thanks so much for watching. Don't forget to subscribe, like, share, and comment. Bye-bye.